Hello guys, myself Assistant Professor Gaurang Prajapati from Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. So, today I am going to cover the chapter of thin cylinder of the subject Structural Analysis 1, 4th Sem Civil Engineering. So, this is the weightage of the chapter in all the previous examples from May 2015 to November 2019. You can see over here. Okay, so on an average the weightage of this chapter in the GTU examination is 7 marks. Now over here you can see the theory summary of the chapter which has been asked in the exam from this chapter, and over here you can see the examples of the chapter which have been asked in the exam, okay, which have been solved in all the examples in this video. Okay, so let's start first of all with the theoretical content. So, introduction. Now, cylindrical and spherical vessels are used in the engineering field to store and transport fluids. Such vessels, tanks, boilers, compressed air receiver, pipelines, etc. So, in the civil engineering, or we can say in engineering field, see, cylinders are always used to store and transport the fluid. Okay, these vessels, once empty, are subjected to atmospheric pressure internally as well as externally, and the resultant pressure on the walls of the cell is nil. So ultimately these cells are subjected to internal as well as external pressures. But whenever vessel is subjected to an internal pressure due to, we can say, air, water, steam, etc., its wall are subjected to tensile stresses. Okay, so whenever internal pressure is there, so ultimately that will subjected to tensile stresses. Now two kind of cylinders are there, say thin cylinder and thick cylinder. Say for the condition for them are this one: when the thickness is less or equals to d by 10 to d by 15, it's called the thin cylinder cell. Okay, and when the thickness is greater than d by 10 to d by 15 is known as thick cylinder cell, where in this case the unknown criteria are T stands for thickness of cell and D stands for internal diameter of the cell. Okay, in thin cylindrical cells, hoop stress and longitudinal stresses are constant over the thickness and radial stresses are negligible. So ultimately in case of the thin cylindrical cell, two kind of stresses are produced: hoop stresses and longitudinal stresses. So let's talk about those two stresses. See over here we can see stresses in the thin cylindrical cell. So two kind of stresses are there: hoop stress and longitudinal stress. So let's talk about first of all hoop stress. Just a minute. See, now talking about hoop stress. See over here you can see in this figure, whenever, let just me zoom in the figure, just a minute. See, whenever you cut any cylinder with respect to its diameter, say if I draw the cross section of this one, I am cutting down this from the diameter point of view. So the upper portion is, we can say, this one, while the lower portion is, we can say, this one. So whenever you cut any cylinder from with respect to diameter, the stresses produced in the cylinder are known as hoop stress, or we can say circumferential stresses. Okay, or we can say tensile stresses also. So in such kind of cases, say formula for the hoop stress, or it is also known as circumferential stress. The formula stands for sigma c equals to pd divided by twice t, where p stands for pressure, d stands for diameter, and t stands for thickness of cell. And in case efficiency is given, okay, so in case of efficiency the formula stands for sigma c equals to pd divided by twice t nc, where nc stands for, that is, efficiency of the circumferential joint. Okay, now let's talk about the another stress, that is longitudinal stress. Now as you can see in the figure, we are cutting down the cylinder with respect to its length. See, this one is our length, so we are cutting down with respect to length, we can say. Okay, so in such kind of cases the stresses produced are known as longitudinal stresses. Okay, the formula for the longitudinal stress is sigma L equals to PD divided by 40, and if efficiency is given, then this formula will be converted into PD divided by 40 into efficiency L, where efficiency L, or we can say eta L, equals to efficiency of longitudinal joint. So we have shown two formula. Number one, that is, we can say circumferential stress, that is PD divided by twice t. Okay, and another, that is longitudinal stress, The formula stands for PD divided by 40. So these are the two formulas which will be used for the longitudinal stress and hoop stress. Okay. Now let's talk about the another term, that is change in the dimension of thin cylindrical cell due to internal pressure. Now because of application of the pressure, the dimensions of the thin cylinder will be get changed. So for that one, the formula which we will be using in this are, see over here. See, change in the diameter, the formula stands for delta D equals to epsilon 1 into D. Okay, and change in the length, the formula will stands for delta L equals to epsilon 2 into L. So in these formulas, unknown parameters are epsilon 1 and epsilon 2. These are the unknown parameters. So this the formula for the epsilon 1 and epsilon 2 are given over here, where epsilon 1 is known as circumferential strain. The formula stands for delta D by D, or we can say ultimately it will formula will be sigma C by E minus sigma L upon ME. While epsilon 2 stands for longitudinal strain, formula stands for delta L by L, and ultimately the final formula will be sigma L by E minus sigma C divided by ME. Now in these formulas, the main formula are this one for epsilon 1 and for epsilon 2, that is this one, sigma L by E minus sigma C by ME. Now the unknown parameters, sigma L, that is longitudinal strain, then sigma C, that is circumferential stress, or we can say hoop stress, then E, that is modulus of elasticity of steel, that is 2 into 10 raised to 5 normal criteria, and 1 upon M, that is known as Poisson's ratio, or it is also known as mu. Okay, so these are the unknown parameters. Once we get the value of epsilon 1 and epsilon 2, then we can easily find out the formula of this one, that is this one. Okay, put down the formula epsilon 1 and epsilon 2 over here in this equation, you will get the value of delta D and delta L. So these are the change in dimensions, say in case of diameter as well as length. Okay, now then the next one, that is change in the volume of the thin cylindrical cell. See, now in this one, because of the volume, what kind of changes will be there because of pressure? In case of volume, so formula will be delta V equals to epsilon 2 plus 2 times epsilon 1 whole multiplied by V. Okay, now in this one, epsilon 1 and epsilon 2, these are the formulas which we have already seen above, that is delta D by D and delta L by L, while epsilon 1 and epsilon 2 are known as circumferential strain and longitudinal strain. Okay, now the maximum shear stress. Now the maximum shear stress formula will be, we can say sigma C minus sigma L by 2, where sigma C, that is PD by twice T, sigma L, that is PD by 4T divided by 2. So ultimately by simplification we will get the formula PD divided by 8T. Okay, or you can directly remember the formula, this one, tau max, that is maximum shear stress equals to sigma C minus sigma L by 2. So these were the cases of the thin cylindrical cell. Now let's talk about the spherical cell. Now over here you can see the figure, spherical cell, when the diameter varies with respect to length. So in this one, two formulas will be there with respect to change of diameter as well as we can say volume. So with respect to diameter, the formula stands for delta D by D equals to, that is PD by 4T in the bracket 1 minus 1 upon M. While in case of the volume, the formula stands for pi into PD raised to 4 divided by 8T in the bracket 1 minus 1 upon M. So these are the formulas which will be used during the examples. Okay, so now let's solve the examples. Now the first example, a thin cylindrical cell with internal diameter 150 mm and wall thickness 15 mm is subjected to a steam pressure of 12 Newton per mm square. Find circumferential and longitudinal stresses in the cell material. It has been asked in 3 marks, May 2017. So first of all, let's write down the data which is given in the day. Okay, so first of all, internal diameter is there, that is of 150. So diameter, that is 150. Then thickness, that is given 15 mm. So T, that is 15 mm. And steam pressure, that is 12 Newton per mm square. So pressure small p stands for 12 Newton per mm square. Find circumferential and longitudinal stresses. So sigma C and sigma L, that is unknown for us. Okay, so now we have seen in the theory, in case of the hoop stress, the formula stands for sigma C equals to PD divided by twice T, where P stands for 12, I'm putting down over here, D stands for 150, putting down over here, and T stands for 15, putting down over here. Now by simplifying this term, we will get the answer, that is 60 Newton per mm square. That is the value of sigma c. Now let's find longitudinal stress. So sigma L equals to PD by 40. Now again all three values are there. P stands for 12, okay. D stands for 150, divide by 4 into T, that stands for 15. By simplifying this term, we will get the answer 30 Newton per mm square. So ultimately by relation you can also say that sigma C and sigma L, by the relation of sigma C and sigma L, I can say sigma L equals to sigma C by 2. Okay, because sigma C's formula is PD by twice T. As you can see, just a minute, see over here, PD by twice T, while this one is PD by 40. So ultimately we can say sigma L equals to sigma C by 2. Okay, you can say like that also, sigma C by 2. Okay, so this was the first example. Now let's solve another kind of examples in this one. Example number 2. A gas cylinder is of internal diameter 1.2 meter and metal thickness 20 mm. Find allowable pressure of the gas inside the cylinder. Okay, if the tensile stress in the material is not to exceed 100 Newton per mm square. Okay, so now let's write down first of all data. Okay, so first of all, diameter is there of 1.2 meter. So diameter 1.2 meter, let's convert it into the smaller units, say multiply by 10 raised to 3. So ultimately 1200 mm. Metal thickness 20 mm. Now thickness stands for 20 mm. Find allowable pressure inside the gas. So ultimately we will calculate pressure. Okay, if the tensile stress in the material is given, that is 100 Newton per mm square. Now this tensile stress means we have already seen in the theory, whenever it is subjected to internal pressure, so ultimately circumferential stresses will be there. So ultimately tensile stress means nothing, we can say sigma c, or we can say hoop stress, 100 Newton per mm square. Now sigma c is given to us, thickness and diameter is given to us, we need to calculate p. Now in this kind of sum, let's sigma c is given, so let's first of all put down the value of equation of sigma c. Sigma c equals to PD by twice T. Now let's put down the value sigma c, that is 100. P stands for unknown parameters. Now diameter is 1200, so let's put down the value 1200, divide by twice, and thickness stands for 20 mm, that is put down over here. Okay, now simplifying this term, we will get the answer P stands for, that is 3.33 Newton per mm square. So this is that kind of example in which one of the stress will be given to you in the data, and you need to calculate any of the three quantity, either we can say pressure, or we can say diameter, or we can say thickness. Okay, any stress sigma c or sigma L will be given to you in the data. Okay, so by applying this, any of these two formulas, whichever is given in the data, you will get any unknown parameters like this. Okay, now let's going forward. Example number 3. A cylindrical cell 500 mm diameter is required to withstand an internal pressure of 4 MPa. Now diameter is given to us in the data 500 mm and pressure, that is 4 MPa. Now P stands for 4 MPa. 1 MPa equals to 1 Newton per mm square. So 4 Newton per mm square. Find the minimum thickness of the cell. Now we need to calculate the thickness of the cell. If maximum tensile strength in the plate material is 400 MPa, once again tensile strength is given to us, that means sigma c is given to us 400 Newton per mm square, and efficiency of the joint is 65%. Now eta is given to us, that is 65%. Okay, take FOS equals to 4, that is stands for factor of safety, that is equals to 4. Okay, now so ultimately this is our given data. Diameter is there, pressure is there, sigma c is there. In this sum, efficiency is also given in the data, as well as factor of safety. So what we need to do now, they have given us sigma c in the data, so ultimately I will apply the formula of sigma c. Sigma c's formula will apply, that is PD divided by, we can say twice T. Now as efficiency is also given in the data, put down the equation of efficiency also over here. We have seen this one in the theory. Okay, whenever efficiency is given, always apply the efficiency over here. Okay, so sigma c equals to PD divided by twice theta. Okay, sigma c, that is 400 Newton per mm square, equals to P stands for, that is pressure, 4 Newton per mm square. Just a minute. Okay, sigma c, that is 400, then P, that is 4. Okay, P, just a minute, yeah, P will be 4 over here. Okay, one correction is there. Then find the D, diameter stands for 500 mm, diameter is 500 mm, divide by twice T, twice, that is constant, thickness is unknown, and eta, that is 65 percentage, means 65 divided by 100, so we can say 0.65. By simplifying this one, we will get this value, that is 3.85, or we can say approximately equals to 4 mm. That is one correction. Okay, instead by mistake I have put down the value of P, that is 2, but it's not 2, it will be, that is we can say 4 Newton per mm square. Okay, now moving forward, example number 4. A boiler cell is to be fabricated from the mild steel plate of 12 mm thickness and has to sustain an effective steam pressure of 1.232 Newton per mm square. Now thickness is given to us, that is 12 mm, okay, thickness 12 mm, and pressure, that is given to us 1.232 Newton per mm square. If the tensile stresses in the mild steel plate must not exceed 106 Newton per mm square. Now the tensile stress is given, so once again sigma c is given to us, that is 106 Newton per mm square. Determine the maximum permissible diameter of the boiler cell. So we need to calculate the diameter in this one. What will be the maximum intensity of the shear stress at any point in the material? So in addition, we need to calculate maximum shear stress, that means tau max. So we are already solving this kind of sums from the last two examples. Okay, pressure is given to us, thickness is given to us, sigma c is given to us, and we need to calculate D. So as sigma c is given to us in the data, so we will apply the formula of sigma c first of all. Sigma c equals to PD divided by twice T. Now sigma c, that is 106 Newton per mm square, P, that is 1.232 over here, diameter is unknown, divided by twice, thickness is 12. So let's put down the value over here. By simplifying this term, we will get the value of D, that is 2064.93 mm. So this is the value of diameter. Now they have also asked the maximum intensity of the shear stress, means tau max. Okay, so now we have seen the formula of tau max in the theory. Tau max equals to, we can say, sigma c minus sigma l divided by 2, or you can also apply the formula PD divided by 80. We have already seen this formula in the theory. Okay, you can apply any of these two formulas, you will get the same answer. Okay, so I am applying this formula, sigma c minus sigma l by 2. Okay, so I already have the value of sigma c in the data, but I do not have the value of sigma l, so I will calculate the value of sigma l first of all for that one. So I have calculated sigma l over here. See, sigma l, that is PD by 40. Now we have the value of P and T in the data. P 1.2032 divided by T, that is 12, and in addition I have calculated the value of diameter over here. So I have put down this value over here, 2064.93. So ultimately I will get the value of sigma L, that is 53 Newton per mm square. I have already told you sigma L will be ultimately sigma c by 2. See, over here value of sigma c is 106 by 2. If you will do this, you will get this value. Okay, and once I get the value of sigma L, now I will apply the formula for maximum shear stress. Tau max equals to sigma c minus sigma l by 2. Sigma c, that is 106, and sigma l, that is 53. So 106 minus 53 divided by 2. So ultimately I will get the answer, that is 26.5 Newton per mm square. And as I told you, you can also calculate the same value by applying the formula PD divided by 80. You will get the same answer like this. Okay, that completely depends on you. Okay, like that. So see, these were the formula. See, in the first example, we have seen the typical kind of example of this chapter, in which pressure, diameter and thickness is given to us. Okay, and we need to calculate sigma c as well as we can sigma l. So these are the values which need to be calculated. While in example numbers 2, 3 or 4, sigma c is given to us in the data. Okay, and out of other three terms, P, D, T, any two terms will be given to us, and we need to calculate and the third one. Okay, like that. Or we can say P and T is given, we need to calculate diameter, or we can say diameter and thickness is given to us, we need to calculate pressure. Okay, so we have covered all kind of examples from this method. So this is the first method in which we need to apply this kind of simple formula. Okay, now example number 5. Now these are the examples which have been continuously asked in the exam. Okay, so now we will solve this kind of examples. First of all, let's see the data. Example number 5. A cylindrical cell 3 meter long, 600 mm diameter with 6 mm thick plate is subjected to an internal pressure of 4 MPa. Okay, so first of all let's write down the data which is given in the, so 3 meter long length is there, so length that is 3 meter long, so let's convert it into mm, so ultimately it will be 3000 mm. Then 600 mm diameter, so diameter is 600 mm. Okay, 6 mm thick plate, so thickness is 6 mm, subjected to internal pressure of, we can say, 4 MPa. So pressure is given to us, that is 4 MPa, that means 4 Newton per mm square. So these are the data. Okay, now calculate number 1 circumferential stress, means sigma c, first one. Second, longitudinal stress, that means sigma L. Okay, and third, change in the capacity of the cell. Now change in the capacity of the cell means we need to calculate its volume, that is delta V. Capacity means its ability to insert, or we can say to store the fluid in it, so ultimately it will be volume. Take E equals to 200 GPa, so E equals to 200 GPa means 200 into 10 raised to 3 MPa. Okay, now 1 MPa equals to 1 Newton per mm square, so ultimately it will be 200 into 10 raised to 3, so let's convert it into 2 into 10 raised to 5 Newton per mm square. Okay, see, you can see over here. And Poisson's ratio, that is 0.3, that is the value of mu, or we can say 1 upon m, that is equals to 0.3 for the material. It has been asked in the 4 marks in November 2019 exam. So now, as I told you, these are the examples which usually ask in the exam. Okay, so these are the data which is given to us, and we need to calculate these 3 terms. So first of all, sigma c and sigma L, we have already solved this kind of examples. First of all, sigma c, hoop stress, or we can say circumferential stress. The equation of sigma c stands for PD divided by twice T. Now we have all these 3 unknowns, P, D and T. Say P is 4 Newton per mm square, you can see 4, diameter, that is 600, so 600 divided by twice T, that is 6, that is 2 into 6. By simplifying the term, we will get the answer, that is 200 Newton per mm square. Okay, so that's the value of sigma c. Then another term, that is sigma L, longitudinal stress. Let's put down its equation, longitudinal stress. Sigma L stands for PD divided by 40. Now P stands for 4 Newton per mm square, diameter stands for 600, 4 into 600 divided by 4, and thickness is 6. Okay, by simplifying this term, we will get the answer, that is 100 Newton per mm square. And earlier also I told you sigma L will be sigma c divided by 2. Say if we do 200 by 2, we will get this answer like that. So we have got the value of sigma c as well as sigma L. So these 2 unknowns have been found out. Now the remaining one is delta V. Okay, so delta V means change in length. So delta V's formula will be over here, change in volume. Delta V equals to epsilon 2 plus 2 times epsilon 1 whole multiplied by V. Now, so for this one we will need 3 unknowns, epsilon 1, epsilon 2 and third volume. Okay, so first of all let's find out the first unknown, volume. So volume stands for area into L. Now as cylinder is of circular section, so circular section's area means pi by 4 d square into L. Now in this one, unknowns are diameter and length. Now all the unknowns are there. Diameter is 600 mm, you can see pi by 4 600 square, and L, that is 3000 mm. Let's solve this one. So ultimately I will get the value 848.23 into 10 raised to 6 mm cube. So I got the value of the volume over here. Now the another unknown is epsilon 1 and epsilon 2. So let's solve first of all epsilon 1. We have seen this formula in the theory. Epsilon 1 stands for sigma c by E minus sigma L by ME. Now the unknown parameters. First of all, sigma c, that is given to us 200. Sorry, we have calculated this one. Sigma c, that is 200 divided by E, that is modulus of elasticity of steel, that is 2 into 10 raised to 5, minus sigma L, that is 100. Let's put down over here 100 into, divide by E. E stands for again 2 into 10 raised to 5, and 1 upon m, that will stands for mu, that is Poisson's ratio. So ultimately 1 upon m means it will multiply with sigma L. So 1 upon m, or we can say mu, that is given to us 0.3. So it is multiplied over here 0.3. Okay. Now by simplifying this term, we will get this answer, that is 8.5 into 10 raised to minus 4. Okay, as it is a strain, so ultimately it will be unitless. Now that's the value of epsilon 1. Now let's talk about the another unknown, that is epsilon 2. Now epsilon 2 is given to over here. Epsilon 2 stands for sigma L by E minus sigma C by ME. We have all the values. Sigma L 100, see, divide by E, that is 2 into 10 raised to 5, 2 into 10 raised to 5, minus sigma C, that is 200, okay, divide by E, that is 2 into 10 raised to 5, and 1 upon M, that will be multiplied over here, that is 0.3. By simplifying this term, we will get the answer, that is 2 into 10 raised to minus 4. So ultimately the unknowns of this volumes formula, volume, epsilon 1 and epsilon 2, we have got all these three values. So let's put down all these three values in this equation. Okay, so say delta V equals to, in the bracket, epsilon 2 plus 2 times epsilon 1 into volume. So first of all, epsilon 2, the value of epsilon 2 is 2 into 10 raised to minus 4, okay, plus 2 times epsilon 1, that is 2 times 8.5 into 10 raised to minus 4, and whole multiply by volume, that is this one, 848.23 into 10 raised to 6. Now by simplifying this term, we will get the answer 1.61 into 10 raised to 6 mm cube. Now let's convert it into the liter. Okay, so ultimately I will get the answer 1 liter equals to 10 raised to 6 mm cube. So ultimately I will get the answer 1.61 liter. Okay, so that is the change in the capacity of the cell, we can say. Okay, so in this example, what we have found out, the change in the volume, okay, as well as hoop stress and longitudinal stress. See, if in the data, if they have not asked us to calculate hoop stress and longitudinal stress, then also we need to calculate this one, because without the value of sigma C and sigma L, we can never calculate the epsilon 1 and 2, and epsilon 1 and 2 are essential for calculating delta V. Okay, so whether they have asked us or not, we need to compulsory calculate sigma C as well as sigma L in this kind of examples. Okay, so this was the example. Let's solve another. Now let's solve the another example, that is example number 6. A cylindrical cell 3 meter long, and length is given to us, that is 3 meter, that is 3 meter. Let's convert it into mm, that is 3000 mm. 1 meter internal diameter is given 1 meter, that's converted into mm, that is 1000 mm, is subjected to an internal pressure of 1 MPa. Now pressure is given to us 1 MPa, that means 1 Newton per mm square. If the thickness of the cell is 10 mm, now the thickness is given to us, that is 10 mm. Find circumferential and longitudinal stresses, means sigma C and sigma L. Find also the maximum shear stress, that means tau max, and change in the dimensions of the cell. Now change in the dimensions means we can say change in volume, change in diameter, as well as change in length. So these are the changes we need to calculate. While in the previous example they have asked us only change in the capacity of the cell, means only delta V. Okay, Poisson's ratio, that is 0.3, that's the value of mu, and modulus of elasticity, that is 200 GPa, that means 2 into 10 raised to 5 Newton per mm square, as we discussed earlier. Okay, so now let's start it with the first one, that is longitudinal and circumferential stresses. Okay, so let's start first one, that is circumferential, or we can say hoop stress. Formula stands for sigma C equals to PD divided by twice T. Now the value of P, that is 1 Newton per mm square, diameter, that is 1000 mm, that is 1000, divided by twice thickness value is 10 mm, that is 2 into 10. By simplifying this 1000 into 20, so we will get the answer, that is 50 Newton per mm square. So that's the value of sigma C. Now longitudinal stress, that is sigma L, PD divided by 40, again same values are there, P, that is 1, diameter, that is 1000, divided by 4, and thickness value is 10 mm, that is 4 into 10. So ultimately we will get the value of delta L, that is 25 Newton per mm square. So we have got sigma C and sigma L. Now they have asked us, that is we can say maximum shear stress, tau max. So the value of the tau max stands for sigma c minus sigma L by 2. We have already used this formula in the above example. Sigma c, that is 50, sigma L, that is 25. 50 minus 25 divided by 2. So ultimately we will get the answer, that is 12.5 Newton per mm square. Or else, as I told you earlier also, you can calculate tau max also by using the formula PD by 8T. Okay, you will get the same value as this formula. Okay, so we have calculated all three first terms, sigma c, sigma L and tau max. Now they have also asked us to calculate the change in volume, change in diameter, change in length, means change in dimensions. So for that one, change in volumes formula is, that is epsilon 2 plus epsilon 1 into V. While change in diameter, we have already seen this formula in the theory, that is epsilon 1 into D, and change in length, that is epsilon 2 into L. Now let's talk about the unknown parameters. Say in this one, that is volume, epsilon 1 and epsilon 2. In this one, epsilon 1, while in this one, epsilon 2. Value of D, L, those are given in the data. Okay, so ultimately we will calculate first of all volume, epsilon 1 and epsilon 2, like previous example. So first of all, let's apply the equation of volume. Volume stands for area into L. Now as for the circular section, cylinder is circular, so area will be pi by 4 d square into L. Now let's put down the value, pi by 4 d square. Now the value of the diameter is 1000, so pi by 4000 square into L, that is 3000. Okay, so ultimately by solving this term we will get the value of volume, that is 2356.19 into 10 raised to 6 mm cube. So value of volume has been derived. Now epsilon 1, the formula stands for sigma c by E minus sigma L by ME. Sigma c, that is 50, divided by E, that is 2 into 10 raised to 5, minus sigma L, that is 25, and Poisson's ratio will be multiplied as part of 1 upon m, like that. So that is 0.3. 25 into 0.3 divided by 2 into 10 raised to 5. By simplifying this one, we will get the value of epsilon 1, that is 2.1 into 10 raised to minus 4. Okay, then epsilon 2, formula stands for sigma L by E minus sigma c by ME. Sigma L, that is 25, by E, that is 2 into 10 raised to 5, minus sigma c, that is 50, and Poisson's ratio will be multiplied, that is 0.3 divided by E, that is 2 into 10 raised to 5. By simplifying this term, we will get the value of epsilon 2, that is 0.5 into 10 raised to minus 4. So as we have got the value of volume, epsilon 1 and epsilon 2, so let's calculate the change in dimensions. So starting with first one, that is change in volume. Just a minute. Yeah. So first of all, change in volume. The formula stands for epsilon 2 plus 2 times epsilon 1 into V. Now value of epsilon 2, that is 0.5 into 10 raised to minus 4, plus 2 times epsilon 1, that is 2.1 into 10 raised to minus 4. So 2 times epsilon 1, and the value of the volume is 2356.19 into 10 raised to 6. By solving this term, we will get the value of delta V as 1.12 into 10 raised to 6 mm cube. Let's convert it into liter, multiply by 10 raised to minus 6. So we will get the final answer, that is 1.12 liter. So that's the change in volume. Now next, that is change in diameter. Formula stands for delta D equals to epsilon 1 into D. Epsilon 1, 2.1 into 10 raised to minus 4, and the value of the diameter is given to us in the data, that is 1000 mm. So by simplifying this term, we will get the value of delta D, that is 0.21 mm. Okay, and last one, change in length, that is epsilon 2 into L. Epsilon 2, 0.5 into 10 raised to minus 4, and L, that is given to us in the data, 3 meter, or we can say 1000 mm. So ultimately we will get the value of delta L, that is 0.15 mm. So ultimately this sum includes change in all dimensions, means length, volume, as well as diameter. Clear? As well as in addition we have also calculated tau max. So ultimately this sum includes one of the all unknowns of the chapter. Okay, so pay attention for the example number 6. If you can solve this example number 6, then probably you can solve each and every sum of thin cylinder. Okay, so now let's move towards the another kind of cylinder, that is spherical cell. That is example number 7. A thin seamless spherical cell. Okay, I have already shown you the spherical cell in the theory. See this one, well, diameter is not completely steady like that. So let's solve the sum first of all. See, a thin seamless spherical cell 1.5 meter diameter. So diameter is 1.5 meter. Let's convert it into mm. That is 1500 mm. 8 mm thick. Thickness is given to us. That is 8 mm. It is filled with a liquid so that the internal pressure is 1.5 Newton per mm square. So the value of the pressure is given 1.5 Newton per mm square. Determine the increase in the diameter and capacity of the cell. So we need to calculate ultimately change in diameter as well as change in volume. Okay, delta D and delta V. Take E, that is 2 into 10 raised to 5, that is modulus of elasticity of cell, and 1 upon m means Poisson's ratio, that is 0.3. So these are the unknowns. Now in case of the spherical cell, we have already seen this formula in the theory. Just a minute, let me show you this one. Over here you can see spherical cell. Okay, so this is the formula for change in length and this is the formula for change in volume. So first of all, change in diameter. Okay, formula stands for delta D by D equals to PD by 40 in the bracket 1 minus 1 upon m. We have all the values. See, first of all delta D, so D will be multiplied with this term. Okay, so formula will be converted into this one. Now for this one, let's put down the unknowns value. Say D, that is 1500. Now in the bracket P stands for 1.5, then diameter again, that is 1500 divided by 4, thickness that is 8 mm, and E, that is 2 into 10 raised to 5. Okay, whole multiply by 1 minus 1 upon m, that is mu 0.3. Okay, so ultimately by solving this term we will get the value of delta D, that is 0.369 mm. So this indicates the change in the diameter. Okay, now just let's calculate change in the capacity, or we can say change in the volume. Formula stands for PD raised to 4, pi into PD raised to 4 divided by 80 in the bracket 1 minus 1 upon m. Let's put down the value pi. Now P stands for 1.5. Okay, diameter stands for 1500 raised to 4 divided by 8, thickness that is 8, and E, that is 2 into 10 raised to 5 in the bracket 1 minus 1 upon m, that is 1 minus mu, that is 1 minus 0.3. By solving this term I will get the value of delta V 1.304 into 10 raised to 6 mm cube. So let's convert it into liter. So 1.304 liter. Okay, so this is the case of spherical cells. See, whenever the spherical cells example ask, you need to apply this change formula, means change of volume, or we can say change in diameter. It is different than previous one, that is of thin cylinder. Okay, now see, this is the example which have been asked in the exam. So let's solve these examples now. Example number 8. Just a minute. See, a thin cylindrical cell is of spherical cell. So first of all, concentrate on this one. Now is of internal diameter 1 meter. Now diameter is 1 meter, so 1000 mm. Cell thickness is 15 mm. So thickness is given to us, that is 15 mm. Determine the pressure that can increase its volume by 80 into 10 raised to 3 mm cube. Now we need to calculate the pressure, okay, which increase its volume, means the change in volume is already given to us in the data, that is 80 into 10 raised to 3 mm cube. Take E, that is 200 GPa, and 1 upon m means mu, that is 0.3. So these are the things which is given to us in the data. So we need to calculate pressure, and they have given us, that is change in volume, means delta V. So we will apply obviously the equation of delta V. Okay, see, delta V equals to pi into P raised to 4 divided by 80 in the bracket 1 minus 1 upon m. Now put down the value delta V, 80 into 10 raised to 3, pi constant, P unknown, diameter that is 1000, so 1000 raised to 4 divided by 8. Now value of the thickness, that is 15, E, that is 2 into 10 raised to 5, and in the bracket 1 minus 1 upon m, that is mu 0.3. So 1 minus 0.3. By simplifying this one, we will have only one unknown in the equation, that is P. So ultimately we will get the value of P, that is 0.87 Newton per mm square. Okay, And now moving forward the next sum, same kind of sum but with some variation. Example number 9. A thin sphere 1.2 meter diameter, now diameter is 1.2, so 1200 mm, is filled with the fluid which exerts internal pressure of 3 MPa. Now in this example pressure is given to us 3 MPa. Calculate the thickness required. Now this time we need to calculate the thickness, that means T. For the sphere, if the change in the volume is not to exceed 1.5% of the original volume. Now in the previous example they have given us change in volume directly in terms of the digit. Now in this one they have not given to us volume directly, change in volume. They have told us that the change in the volume that will be 1.5% of the original volume. Okay, so we need to calculate thickness for this kind of example. So now first of all let's talk about the unknown. Now we need to calculate first of all thickness, and they have given to us delta V in terms of the volume. So first of all we need to calculate the volume. So let's calculate first of all volume. Now as it is a spherical cell, so ultimately the equation of the volume will be pi by 6 d cube. Okay, now diameter is 1200, so pi by 6 into 1200 cube, so ultimately we will get the value of volume, that is 904.78 into 10 raised to 6 mm cube. Okay, now they have told us that the change in volume will be 1.5% of the original volume. So now we will calculate the first of all change in volume from this value. Okay, delta V equals to 1.5% of the volume, so 1.5 divided by 100 into this value, that is 904.78 into 10 raised to 6. So ultimately we will get the value of delta V, that is 13.157 into 10 raised to 6 mm cube. Once we get the value of delta V, now I can apply the original formula, change in volume. Delta V equals to pi into p raised to 4 divided by 80 in the bracket 1 minus 1 upon m. Now delta V, that is 13.57 into 10 raised to 6 equals to pi, now pressure, that is 3, diameter, that is 1200 raised to 4 divided by 8, thickness is unknown, and E, that is 2 into 10 raised to 5 in the bracket 1 minus 1 upon m. 1 upon m is, we can say mu, that is 0.3. Okay, by simplifying this one we will get the unknown value, that is the value of thickness, that is 0.63 mm. Okay, so the difference between these two examples is, in the above example they have directly given us delta V 18 to 10 raised to 3, while in this one what they have told us that the change in volume is 1.5% of the original volume. So first of all we need to calculate this value. Okay, so these are the examples which have been asked in the exam, as well as I have covered some of the other examples also which has not been asked in the example, but this is necessary for practice. So this is the chapter of thin cylinder. Myself Gaurang Prajapati, signing off. Okay.